Let's see how we can use solute balance to get at base flow in a stream. So a similar way of thinking about base flow is that you have, remember we talked about quick flow and we talked about base flow. And so the water that flows quickly, the water that runs off on the surface and makes it rapidly to the stream, is going to be relatively new water, meaning that it fell from the sky as rain and then made it to the stream pretty quickly. Base flow, which is primarily groundwater, comes from that precipitation that percolates down to the water table and then moves to the stream, and it's going to take a while, which means that water's older. So we have two components of the base flow, Qt. We have the new flow, Qn, and we have the old flow, Qo. Those different contributions to the stream are going to have different chemistry, right? So maybe we can use the chemistry to separate the quick flow with new water and the base flow with old water. So to remind you in our discharge curve, right, if this is discharge versus time, the new water would be the quick flow, which would be sort of flashy, come up and drop off relatively quickly. And then the old water would be base flow, which comes up slowly but also declines slowly. And the sum of those are the total flow in the stream or the total discharge curve that we see here. So let's see how we can do this with chemistry. We're going to balance both the water flow and the concentration of solutes in that. So in this case, the concentrations that we're looking at to understand how our water is flowing is called a tracer. And that tracer that we're going to use in this particular case is chloride. We could use lots of different tracers. Chloride is a particularly good tracer because it doesn't react with the subsurface. It doesn't degrade due to biodegradation. And so we say it's conserved as it moves. It doesn't disappear. So that makes it a good tracer. It's like a dye, right? You put some of this tracer in the water and you can see where the water goes. So let's define our terms. We have the total discharge is Qt. I'll just call that total flow. And then Qn is the new water flow. And Qo is the old water flow. So then we have the concentration of our tracer. So this is water. We have the concentration of our tracer, and that is the total concentration in the stream. And we have the concentration in the stream that comes from new water. And of course we have the old water. So we're going to try and separate out these components of flow using our concentration. Okay, so we already saw that if we balance Q times C, that is a mass flux, right? So let's make use of this. Okay, so first we're going to balance the flow. Right? So we know that the total flow in the stream has to be equal to the old flow plus the new flow. And then we have the balance of the concentrations of the solute. So in this case, we're assuming it's chloride, for example. So we have the total flow times the total concentration in the stream. And then we have the old water flow coming in and the concentration in the old water plus the concentration, the flow in of the new water times the concentration of the new water. Okay? So what we can do is we can use these two different equations. We have two equations that we can work with, And we're going to solve for the volume balance, and we're going to substitute it into the solute mass balance. Okay, so we're going to see that we're going to use the old water is equal to the total flow minus the new water. And then we're going to substitute that in over here. So we have the total flow times the concentration. And now we have the total flow minus the new flow times the old concentration plus the new flow times the new concentration. So notice that we've gotten rid of one of our flow components, which is kind of nice. Okay, so I can rearrange, and we end up with the flow rate of the new water times the difference in concentration of the new and the old, plus the flow rate of the total stream times the concentration of the old water minus the concentration in the total discharge. Okay, and that is going to be equal to 0. All right, and all I did is I just rearranged this equation right here. Okay, so I'm rearranging this equation to get to this one. So I haven't done anything new other than a little bit of algebra. So now I can find the ratio of new water over the total water flow, and that is simply equal to the concentration of the tracer in the total flow minus the concentration in the old water times the concentration of the new flow minus the concentration in the old water. So what we've done here is pretty neat, actually. We've taken what we want, essentially, is the components of the flow, and we can use the concentrations of this tracer in the water to get at the flow. So we're using solute concentration to get at the volume balance. So we'll do a little example and see how this might work.